2.4 Venn diagrams with 3 sets and verification of equality of sets. So in 2.5, we'll get more into like working with 3 sets and applications of 3 sets. But 2.4 is like an introduction to what does it mean to have 3 sets. Okay, so this is what it looks like when we have 3 sets overlapping. So we have set A, set B, set C, and that it creates 8 regions, and it goes top, then left to right. So 1, 2, 3, go to the middle, 4, 5, 6, down 7. And remember, the universal box is always the set itself and a region itself. In this case, it's region 8. You can read through this if you want. It's just describing each set and what it means. I'll kind of like paraphrase it. So the middle, when V is shaded, which is 5, remember that's a 5 in Roman numerals. When that's shaded, that's A intersection B intersection C. So that's where everything connects. That's where everything has in common with A, B, and C. We have region 2 and region 5. That's where A and B meet. Region 4 and region 5 are where A and C meet. Region 5 and region 6 are where B and C meet. 1, 2, 3, 4, 5, 6, that's A union B. 1, 2, 3, 4, 5, 6, I did that twice. All right, 1, 2, 4, 5, 6, 7 is A union C. And then the complement of A union B, B union C, is the universal box, which is region 8. All right, human blood is classified typed according to the presence or absence of a specific antigen, A, B, and Rh, in the red blood cells. Antigens are highly specified proteins and carbohydrates that will trigger the production of antibodies in the blood to fight infection. Blood containing the Rh antigen is labeled positive, plus, while blood lacking Rh antigen is labeled negative. Blood lacking both A and B antigens are called type O. Sketch a Venn diagram with 3 sets A, B, Rh, and place each type of blood listed in the proper region. A person only has 1 blood type. You can't have 2 different blood types. You're only 1 blood type. All right, it's telling us that we have 3 sets. We have set A, we have blood type B, which is set B. And then we have blood type Rh, which is set Rh. And don't forget about your universal box. Our universal box is for what doesn't fit in, so we label that as a U. It tells us something about Rh. It says if it has Rh, we label it positive. So this is positive. That means the outside, the universal box, is not going to be positive. So we're going to be looking for something different there. All right, when we fill in diagrams, Venn diagrams, we're going to start from the center and work our way out. Always start from the center, then work your way out. So if we want to talk about the center, it's where they all meet. And where they all meet, that's A, B, and positive. So AB positive is what's going to go in the center. Because that's in circle A, circle B, and circle RH, which is positive. Cool. All right, we did that one. Now we're just going to keep going on. So now we start working on the outside. So let's go up here on top. This is where A and B meet. But is this AB anywhere near the plus? It's not in the RH, right? It's not in the orange bubble. So this is AB negative. All right, let's just keep going. So here, this is A and RH. So that's ARH, which is A positive. All right, here we're in circle B, set B. and then set RH, or set positive, so that's B positive. All right, now we have A just by itself. So since it has right here, I'm talking about this region right here. Since A is by itself and it's not part of the positive bubble, this is A negative. So this makes this B negative. Now we need to figure out what goes in RH, because we still have blood types. We have O positive and O negative. So if it doesn't have A and B, but it has the positive, we would say that is O positive. So it does contain the RH antigen, so it is positive. Last but not least, on the outside, we have O negative. Because O has nothing to do with A and B, and negative, that means it's not RH. If this is a little tricky, watch it a couple times. I can't show a different example because there's only one example of blood type. I can't change blood types. So watch this a couple times, okay? We're going to do a lot more with three sets in 2.5. Verification of equality of sets. To verify set statements are equal for any two selected, getting tongue-tied today. To verify set statements are equal for any two sets selected, we use deductive reasoning with Venn diagrams. If both statements represent the same region of the Venn diagram, then the statements are true for all sets A and B. So let's look at a set and determine, or let's look at multiple sets and determine if they are equal. So the first thing we're going to do is draw our Venn diagram, because that's how we approach this. We're going to draw a Venn diagram. Because with pictures, we can see things that we normally can't by reading. So since we're only talking about two sets, we have set A and set B. And we're going to label it with the region numbers. So this is region 1, 2, 3, and outside is 4. That's the universal set. All right, now that we did that, let's go ahead and take each of these individually out. So we have A intersection B and the complement of that. And then we have complement A, union complement B. So we're going to break this down individually. We're going to take each little thing out. So we're going to take out A intersection B, and then after that, we're going to figure out the complement. And we're going to figure out what region this is in. So set A is all of region 1 and region 2. That's all of set A. Set B is all of 2 and all of 3. The intersection of A and B is region 2. So now that we have that, we have what is the intersection, which is 2. Every other number is the complement, because remember, the complement is what is not. What's the difference? What's the opposite? It's not. So not 2 is 1, 3, 4, and those are regions we're talking about using our Venn diagram. So this is what we're going to compare to our other side of the equation. So the complement of A union complement B. We're going to see if those match up at the end. All right, so again, we're going to break this up. So we have the complement of A, the complement of B, and then the union of those two complements. So remember, complement is not. So everything that's not A is 3 and 4. Because 2 is in A. See, 2 is in A, so we can't do it. Everything that's not in A is only 3 and 4. Everything that's not B is 1 and 4. So then if we union them, it's 1, 3, 4, those regions. They are the same. So since they are the same, they are equal. And that's all we would say. Yes, they are equal. So you draw your Venn diagram, take each piece out individually, and then your final answer, you compare the regions. And we're about to do that again before, though. We have to talk about De Morgan's Law. De Morgan's Law we're going to use a lot through this semester. We'll talk about it in Chapter 3. So a pair of related theorems known as De Morgan's Laws make it possible to change statements and formulas into more convenient forms. So it's a way for us to work with it to make it easier, so we can change things to make it work for us. It's like, when you add fractions, they have to have the same denominator because it makes it so you can work with it. Kind of similar thing, that we can switch it so we can work with it. So De Morgan's Law is if you have A intersection B, the complement of that, it's the same thing as the complement of A union complement B. And then if you have the complement of A union B, it's the same thing as the complement A intersection complement B. So if we take this one out for a second, just the top one, I want to teach you a trick to memorize this. Complement means not. Like not A, not B. And not is negative. And when you think of math, when you do a negative, it just switches all the signs. So it's kind of what we're talking about here. If we I'm doing little quote fingers, if we distribute, I hope you heard the inflection in my voice, if we distribute that little complement symbol, which means not, then it switches all the signs, just like in normal everyday arithmetic. So if we switch the signs, A becomes not A, intersection becomes union, B becomes not B. And you see how we get our other side? So you can think of it that way. It's also going to come up in Chapter 3, so kind of think of it that way. Is that what we're doing? Absolutely not. It's just a way to think about something, okay? All right, let's do the same thing with 3 sets. So this only works with 2 sets, A and B. So how do we approach something when it's set A, set B, and set C? So the first thing we do is draw a Venn diagram. So we have 3 sets, A, B, and C. And then we label our Venn diagram. This is region 1, 2, 3, 4, 5, 6, 7, and then our universal set is 8. So remember, it goes in order, it goes left to right, and you start at the top. Alright, so we're going to separate each side. So we have A union, B intersection C. We're going to figure out the region of that. And then we're going to do the same thing to our right side. All right, let's break this up individually. So we first have A, then we have B intersection C, then we want to bring it all together with a union. So A, all of A, everything in bubble A, circle A is 1, 2, 4, 5. The intersection of B and C, so where B and C meet, so this is B and this is C. They meet both together at 5 and 6, right here. They meet together at 5 and 6. Now we need to union these. So we need to put all of our numbers together of the regions we already have. So 1, 2, 4, 5, 6. So this is what we're going to compare at the end. All right, let's do it for our next batch of sets. So we're going to break this up into A union B, A union C, and then we're going to bring it all together. All right, so A union B, that means everything in A, everything in B. Put it together. So 1, 2, 3, 4, 5, 6. Everything in circle A, everything in circle B. All right, now let's do A union C. So everything in circle A, everything in circle C. We have 1, 2, 4, 5, 6, 7. Now we need to figure out where they intersect. So where they come together. So 1, 2, 4, 5, and 6. So let's see if they match. 1, 2, 4, 5, 6. They absolutely do. So if you want a way, because, I mean, yeah, you can say yes. But if you want to know the mathy way to say yes, so if you want it to be fancy and say it super correctly, this is how you would actually say this. So instead of saying yes, we could say A union B intersection C equals A union B intersection A union C for all sets A, B, and C. That's a horrible A. There we go.